Very much, Christina, for the introduction, and of course, thanks to everyone for having me, for the invitation. I can say I would be delighted to be in Arizona right now for various reasons. Well, I guess, we have to live with the current situation. And I think it's actually a good opportunity to get together, at least virtually, which wouldn't have been so easy, I guess, if we, we're in different times. So yeah, the title of my talk is Bridging Energy Conversion and Storage in Two-Dimensional Molecular Frameworks. And so, I would like to start out with, okay, hang on. Okay, I'd like to start out, by giving you a sense of the materials that I will be talking about in this presentation, because these materials are obviously the main players. So I like to compare these molecular two-dimensional frameworks as with graphene, and to consider them as heterographenes. So take the graphene lattice, as you see it here, and then take out carbon from the lattice and take back in, or put back in, heteroatoms such as nitrogen or hydrogen, or vacancies in an ordered fashion. And what you will end up with, if you do that, is basically a whole family of 2D molecular frameworks with more or less, heteroatom content and porosity. So for example, covalent organic frameworks and covalent triazine frameworks, which tend to have carbon-carbon bonds and carbon-hydrogen bonds, so they are on the organic side of things. But then if you introduce more and more nitrogen up to the maximum level, actually, you'll end up with graphitic carbon nitride type systems that have a strictly alternating carbon-nitrogen backbone. So this is basically, what you see here is a hypothetical graphitic compound or graphic carbon nitride compound that is based on triazine units with a stoichiometry C3 and 4. What you see here is a polytriazine imide, which is derived from this system here, not as fully condensed. And this is actually a system that exists and that is sort of well known. I'll come back to these carbon nitrides in the second part of my talk, but I will start out by talking a bit about covalent organic frameworks and their use in solar energy conversion. Before I do that, perhaps I should mention why these frameworks are actually so interesting for solar energy conversion, or why we believe that deriving them formally from graphene makes sense. So, graphene, as you know, is a Dirac semi-metal, so it has a number of interesting properties like these linearly dispersed Dirac cones. And if you mess around with this carbon lattice, of course, we're losing some of these properties, like this semi-metal character, but we gain something that graphene does not have, which is a band gap. And so in these systems, we expect to find a band gap. And a band gap, of course, is immediately relevant in optoelectronics and also in solar energy conversion. So basically everywhere where light harvesting is involved. So as I said, before I come to that, let me just briefly introduce you a bit more to carbon nitrides, to covalent organic frameworks, and specifically how we can make these materials, because this is a very special class of polymers. So COFs are 2- or 3-dimensional polymers. And most of the polymers you're aware of are 1-dimensional systems. Also, these COFs are micro and mesopore, so they have ordered structural porosity. And last, but certainly not least, these are crystalline polymers. And this is actually a point that deserves a bit more attention. So how can we make polymers crystalline? So basically what we do is we use reversible bond formation. So typically condensation reactions. And to keep up this reversibility, we need to make sure that the reverse reaction, hydrolysis or ammonolysis, can also take place. And so what this does is it gives us a mechanism of error correction. So we can close and reopen bonds close to thermodynamic equilibrium. And that actually will then sort of help us to reach this ordered crystalline state in these polymers. Okay, so just because there is a mechanism of error correction, of course, does not mean that these systems are, fully ordered or single crystalline. In fact, they are not, because simply this reversibility is not, okay, hang on. The reversibility of bond formation is not, is not perfect. And, I just want to briefly make this point that there's very little known about the real structure of covalent organic frameworks, especially the type of defects and disorder in these systems. And in order to understand this, we need to do imaging, and we need to essentially make sure that we can use, for example, TEM or other imaging techniques on these systems. So recently, we and others have developed post-synthetic modification techniques in order to stabilize these frameworks. So here you can see an imine COF that was transformed into a thiazole COF by sulfurization, which gives them a high beam stability, electron beam stability. And so we are now able to image structural details at a resolution that we haven't been able to achieve previously. So for example, here you can see covalently intergrown grain boundaries in these systems, which seem to be composed of 5 and 7 membered rings. We can see the origins of edge dislocations, for example. And so, understanding these details of the real structure of these systems is extremely relevant in order to understand the properties of COFs. Another example is the third dimension. So there's a common sense that, the in-plane structure of two-dimensional COFs is fairly well understood. We can basically, note it down with a pencil because we know what the building blocks are and how they can combine. But there's very little knowledge in the third dimension, the stacking direction. And basically 2D COFs are typically depicted simply as being layers that are perfectly eclipsed stacked. So right on top of one layer, right on top of each other. But there's also the sense, and that's very obvious, especially I guess to organic chemists, that if you stack aromatic system right on top of each other, this is not the thermodynamic minimum configuration. And so what we did is quite recently we used total scattering analysis, pair distribution function analysis to get an idea of the local structure of covalent organic frameworks. And this actually tells us that although these COFs seem to have a very high symmetry structure, so from the powder XRD, you get very little information. You just see a high symmetry, in that case, hexagonal structure. But when you look closely at the local structure, you'll find that the COFs are much more disordered. And what that basically means, that is sketched here, is that the layers show random translational layer offsets. And so on average, these COFs appear as ecliptically stacked and high symmetry. But the local order, locally they are much more disordered and lower symmetry. And that, of course, has an influence on the effective pore size, for example. And that, again, is relevant for catalysis. So I just want to, sensitize you sort of for these real structure effects that are important to understand in these systems. And that is actually something that, one of the lines of research we're currently pursuing. But now let me come to the actual topic of my talk. I would like to introduce these frameworks for solar energy conversion, and especially the main reaction we're looking at right now is water splitting, and more precisely hydrogen evolution. So we've chosen this reaction not only because it is a highly relevant reaction, obviously, but also because we're dealing with complex materials. And so the reactions we've chosen should be as simple and straightforward as possible. But still, water splitting is, it might seem simple at first sight, but it's actually quite complex nevertheless. So water splitting is composed of two half reactions, the water oxidation reaction and the water reduction reaction, or hydrogen evolution. And it is a thermodynamically uphill reaction by 2.46 eV. How do we arrive at these 2.46 eV? Well, basically, in order to produce 1 mole of hydrogen, we need 2 energetic electrons, energetic by 1.23 eV. So that needs to be sort of the size of the band gap, the minimum size, if we assume an ideal process without any losses. And that corresponds roughly to a wavelength of below 1000 nanometers. You know, 2 of these electrons then give us 2.46 eV. And how do we make these energetic electrons in the first place? We use a semiconductor, a light absorber that absorbs light and then generates an electron-hole pair. And these charge carriers are then shuttled to the surface where they are used for the reduction and the oxidation half reaction, typically in combination with a co-catalyst. So this is, you know, this process looks quite simple and straightforward, but, you know, nothing is as simple as it seems. And also this process is actually quite complex. The requirements for what I've just shown you is basically a sequence of steps that start out with the generation of an electron-hole pair by the semiconductor. So we need a light harvester essentially that generates the charges. In the second step, we need to separate these charges, somehow, you know, get them apart. Then the charges need to be transported or percolate to the surface, to the solid electrolyte interface or the contacts where they're extracted. And finally, we need an efficient catalytic conversion at the surface. So the efficiency of this overall process is basically the product of the efficiencies of these individual steps. And so we want to make sure that each of these steps is as efficient as possible. And so at this stage, I guess it makes sense to zoom out a bit and compare organic semiconductors, which is the topic of the talk, with classical inorganic semiconductor photocatalysts and see, you know, how they compare. And so this is a slightly convoluted graphics, but, you know, the take-home message here is basically that when we, you know, compare band gaps and light harvesting ability in these systems, in inorganic and organic systems, they are quite comparable. So, you know, there's not a huge difference. We can tune them. You know, there's quite a bit of degree of freedom here for adjusting things. However, things get different when we look at other factors like charge carrier concentration, dielectric constants, effective hole and electron masses, and also exciton binding energies. So just to give you an idea, in inorganic systems, excitons are often 1E mod type excitons that are rather, you know, loosely bound and can, you know, easily be separated. This is very different in organic systems where we typically have strongly bound excitons, Frankel type excitons, that are very difficult to separate simply because they have high exciton binding energies. The reason is typically low dielectric constants in these systems with little screening of the charge carrier. So they, you know, stick together. And it's difficult to separate them. Also, charge carrier mobilities are very different in inorganic and organic systems. In inorganic systems, often we have much higher charge carrier mobilities than in organic systems for intrinsic electronic reasons, but also because organic systems, especially polymers and amorphous systems, are loaded with traps that, of course, slow down the charge carriers. Also, we cannot take advantage of band bending that we see at the solid-liquid interface in many inorganic systems, simply because we have very low amounts of free charge carriers in organic systems. And therefore, you know, there's no sort of driving force or additional driving force to separate the charges at this interface. So what we need to do, and this is basically the photocatalytic reality here, we need to come up with ways of efficiently separating the charge carriers in organic systems, basically right where they are formed. And we can do that, for example, by making the system porous, by making it accessible, by you know, constructing bulk heterojunction type systems where we maximize the number of interfaces across which we can then separate the charges. And so, you know, looking at what I've just said, basically, you might ask yourself, well, why then looking at organic systems for photocatalysis at all if they perform so badly or compare so badly to inorganic systems? Now, the answer is, and here, of course, specifically for COFs, the answer is that on the structural level, and also, in terms of tunability, these covalent organic frameworks have a lot to offer. So basically what you can see here is that they have highly ordered structures, which could be understood as, highways for charge carriers that can easily travel basically in all directions. We have a bimodal type structure where we could think of internal heterojunctions. We could put something in the pores, for example, an acceptor. And in any case, these systems are highly porous and very well accessible to the electrolyte. So that actually makes them very useful and interesting for catalysis. And also, there's a big trend towards single-site photocatalysts or catalysts in general. And if you think about it, covalent organic frameworks or also carbon nitrides are molecularly precise systems. And so in a sense, if we get rid of these nanoparticulate co-catalysts, which we typically use, I'll come back to that a bit later, and substitute them by molecular co-catalysts, we can actually arrive at all single-site heterogeneous photocatalysts, which is quite intriguing. Okay, so in the next couple of slides, I would actually just like to walk you through our initial and also current steps towards developing such COFs for photocatalysis. And so basically, so this is a little and quick summary. So basically, we presented the first COF for photocatalytic hydrogen evolution in 2014. So until that time, COFs had actually, and interestingly, never been used for photocatalysis. And it's great to see that this field really now is exploding. So this first COF, photocatalytically active COF, was a hydrosome-based COF. So here you see it's a mesoporous system based on this triazine building block here. And in a nutshell, we could show that the system is active for hydrogen evolution in the presence of a sacrificial electron donor and a co-catalyst platinum. And we achieved quantum efficiencies around 2% that were at that time competitive with those in carbon nitrides. So that was the first proof of concept. Of course, then we wanted to take full advantage of the tunability of covalent organic frameworks, because after all, this is the hallmark of COFs. And so what we did is we designed an azine COF platform composed of 4 members, and these members only differed in sort of these building blocks here, where the building blocks differ by the number of nitrogen atoms that are inserted into the central aryl ring. So going from phenyl or triphenyl aryl without nitrogen in the central ring to the pyridine and pyrimidine and triazine system. And as we do that, we're sort of flattening out this twisted building block. So here, this is a very twisted building block that also translates in the structure of the COF. And we're flattening this out towards this triazine system here. And we notice that that actually directly translates into the structure of the COF. So we're seeing, as we go from top to bottom, we see a planarization of the system. We see an increase in crystallinity and structural definition. Also, we see an increase in porosity on going from the top to the bottom. And we see a difference in electronic character as well. So as we introduce nitrogen, the system gets more electron poor and therefore is able to stabilize the radical anion that we believe is formed as an intermediate during photocatalysis. And we have also evidence that this indeed happens. And so, the bottom line is that for these systems, as we introduce nitrogen into the ring, we see an increase in the hydrogen evolution efficiency by a factor of 4 for each nitrogen that we add to the ring. And so that really sort of reassured us that we can use the tunability of COFs at the molecular level to really tune the photocatalytic activity in these systems. So the next task basically was to get rid of the platinum co-catalyst and replace it ideally by something earth abundant and also by something molecular, so that we get better insights into the photocatalytic mechanism as such. And so a very brief summary here, if you're interested in that, of course, I'd be happy to discuss that after the talk. So our first attempt was basically to just hybridizing the COFs with a molecular co-catalyst, a cobalaxine co-catalyst. So these are, very well-known electrocatalysts for the hydrogen evolution reaction. And we simply, put them into the suspension of the COF. And what we saw is that we see quite stable and continued hydrogen evolution with this cobalaxine catalyst that is actually more efficient than using platinum in the system. I should say, though, that we optimized, of course, for the cobalaxine. And this is actually a bit of a problem because the catalysis then only works in an acetonitrile water mixture of water 1 and not in pure water. And so that's something, of course, we wanted to tackle and change. And so we developed this system here, a thiazole COF that we combined with a nickel, hexameric nickel cluster co-catalyst that is actually assembled in situ. And so this system here works in pure water. It works very stably. It's actually even more efficient than this cobalaxine system here. And so we modeled the reaction by using microkinetic model. And so what we found out is that, and this is not too surprising, that the electron transfer step from the COF to the co-catalyst is the rate limiting step most likely. And so this can be understood because we don't have any permanent contact between the co-catalyst and the COF, because simply the co-catalyst is in solution. We need conditions between the COF and the co-catalyst for the charge transfer to happen. And so we figured that what happens if we somehow attach the co-catalyst to the COF, or somehow make sure that there is a permanent close contact. And so we developed a system based on COF42, where we functionalized a cobalaxine co-catalyst with an azide group, and then we clicked this azide functionalized co-catalyst to a proper gel functionalized COF42. And so that actually gives loadings that are not ultra high, so a couple of weight %. But as you'll see, this is actually quite the right ballpark to actually achieve good catalytic activities. But of course, we wanted to make sure first that we have evidence actually that there is a contact between, or a coupling between the COF and the co-catalyst. And so solid state NMR was actually a very helpful technique to verify this. So what you see here are double quantum, single quantum proton NMR measurements. So these probe the dipolar couplings between protons that are close to each other in space. So roughly, below 3 to 4 angstroms. And so I'd like to just, make you aware of this little off-diagonal cross peak here, which is actually showing us that this glyoxine proton couples or is in close contact with this ethoxy group in the pore wall. And so that actually tells us that there is a close and permanent contact between the two, which makes sense because we're covalently coupling the two. This is also supported by other NMR techniques, for example, a T1 weighted direct polarization 13C measurement that probes the dynamics of the co-catalyst in the pore. And what we see is that the co-catalyst is fairly rigid. So this is quite consistent also with MD simulations that told us that there is, most likely a contact between the co-catalyst and the pore wall. And so what does that mean for catalysis? So this is shown here, where we compare now a physisorbed cobalaxine catalyst with the chemisorbed catalysts And you see that the behavior as a function of covaloxime content is quite different. So for the physisorb systems, we see this saturation type behavior, but we see that there is a maximum in catalytic activity, in hydrogen evolution activity for the chemisorb system. So basically that tells us that there's an optimum, a sweet spot of catalyst loading. And if we go higher, then there's poor clogging, and too low is, obviously also reduces the activity, which makes sense. What we also see, and that is quite interesting, is that the activities can be higher for the covalently bonded system. This trend also is maintained in long-term stability. So as expected, basically, the covalently coupled system is more stable, more durable than the physisorb system, which deactivates much earlier. We believe, or we think, that this could actually be, at least in part, due to confinement effects. In covaloxime hydrogen evolution catalysis, in the intermediate stage, the axial ligand of the covaloxime needs to come off actually, and then needs to coordinate back on the cobalt during catalysis. And if the axial ligand is lost, the catalyst is deactivated. And so we believe that perhaps in the pore of the COF, this coming off and going back on might be facilitated. So that this is a possible interpretation of this better long-term stability. Okay, so now let me switch gears and move over to the carbon nitride side. So what I've shown you so far is our activities on COF-co-catalysis or hydrogen evolution photocatalysis. And I'd like to now contrast this basically with hydrogen evolution catalysis with carbon nitrides, and show you what else we can actually achieve or do with these carbon nitrides, because although you could consider them as covalent organic frameworks in a sense, their chemistry is actually quite different. And so the system that I will be talking about now is polyheptazine imide, PHI. So this is a two-dimensional system. So just imagine that this is a fully condensed in the plane, fully condensed heptazine-based system. And this is one of the few truly two-dimensional carbon nitrides. The typical carbon nitride that is simply and loosely termed C3N4 or graphitic carbon nitride is actually a one-dimensional heptazine-based polymer that was synthesized for the first time by Justus von Liebig about 200 years ago, and was called melon. For no obvious reason. So keep in mind that this one-dimensional carbon nitride polymer is called melon and is basically the benchmark carbon nitride, also the one that we compare this two-dimensional system to. So this material is obtained not by the typical solid gas reaction, which is normally used for carbon nitride synthesis, but by an ionothermal synthesis from, let's say, nitrogen-rich precursors in various types of salt melts. As I said, it is a heptazine-based system, and it is highly electron deficient, or one could say it has a very low-lying valence band and conduction band. So in other words, this is not only a very inert system, but it also has a very large driving force for hole extraction or for water oxidation, for example. So for oxidation reaction, it is, once photoexcited, it has an extremely high oxidative power. And remember that, although we are now looking at the hydrogen evolution reaction, this driving force for hole extraction, we believe, is extremely relevant also for these hydrogen evolving systems. I'll come back to that in a minute. So, first of all, what we did is we compared this PHI type carbon nitride with the classical melon type carbon nitrides. And as you see here, the band gap is essentially the same, 2.7 eV. But when you look at the hydrogen evolution activity of this PHI, then you see that it is it vastly outperforms Melon-type carbon nitrides by about, a factor of 20 or so. So we are achieving quantum efficiencies, let's say around 15 to 20%. So that's quite substantial. And we were wondering actually, where does this difference come from? And I can tell you, we still haven't fully understood why this is so different, but I hope that at least, I can show you that there are a couple of peculiar things going on in the system that are very different from Melon-type carbon nitrides. Okay, so in order to understand where this activity comes from, we went back a step and looked at the structure of this material, because we very much believe that the structure is actually at the heart of the properties of the system. So we need to understand the structure first. So here's a TEM image. You see a layered morphology and particle sizes. This is a very nice, actually, a very nice sample. Particle sizes are around, let's say, lateral sheet extensions around 80 nanometers to a couple of hundred nanometers. Now, TEM, electron diffraction tells us that this is a crystalline system, a nanocrystalline system. So we don't have single crystals, but we can clearly use the crystallinity for structure solution. Combining with powder X-ray diffraction, we came up with a structure model that shows us, it is a 2D heptazine-based system, but not only heptazine-based, but there's actually, and you've probably spotted this already before, we have an alkali metal ions, here potassium, sitting in the pores, and these alkali metal ions are hydrated. Local structure analysis, pair distribution function analysis, and also state NMR tells us that this potassium ion is actually sort of not sitting in the center of the pore, but it's offset towards the carbon nitride backbone. So there's likely an interaction with the carbon nitride backbone. And we have a lot of diffuse electron density in the pore. So, it's a highly hydrated system. What we can also say is that the potassium ions are obviously, we believe instrumental in determining the stacking structure of the system. So you can see here, it's pseudo-hexagonal, trigonal, when we just look at one single layer, but this is a triclinic system because simply we have this, this offset type layer stacking. Now, interestingly, the potassium ions, hydrated potassium ions, are not only structure directing, but they are actually also mobile. So we made potassium PHI and also the homologous series, so other alkali metal PHIs. And so what we observe is that we see predominantly ionic conductivity in these systems. So the hydrated ions are mobile with conductivities up to round about 10 to the minus 6, 10 to the minus 5 Siemens per centimeter, depending a lot on the hydration state of these hydrated alkali metals. So, as we ramp up the humidity, the conductivity goes up, actually up to roughly about 10 to the minus 3 Siemens per centimeter. And we believe that, these differences in conductivity that we see, so the highest conductivity is observed for the sodium compound, really correlates with the hydrodynamic radius of the system combined with the stacking polytype in these systems, which is actually different for the different alkali metal ions. Now, let me now come to the optoelectronic properties of these systems. Now we've looked at the structure, at the dynamics of the ions, and now we look at the optical or optoelectronic properties. And so, in a nutshell, what you see here are transient absorption spectroscopy measurements that were done in James Doran's group in London. And here we are comparing PHI with Melon in the presence of a sacrificial electron donor for MBA, methyl benzyl alcohol, or without the presence of the sacrificial electron donor. And remember that this electron donor is used in photocatalysis to quench the holes. Now, we see that the intrinsic decay of the two, of Melon and PHI, is very similar. But this changes a lot when we add the sacrificial electron donor, because then we see a very long-lived component coming up here for PHI. And this spectral component is actually consistent with trapped electrons. So that is a very well-known signature of these trapped electrons on the carbon nitride backbone. And that tells us that the whole transfer reactivity, so that the whole extraction in the system is extremely fast. So holes are extracted very easily, and that is actually due to the fact that the system has a very low-lying valence band, so it's very oxidative. It takes up electrons very easily, or oxidizes the electron donor, and the photoexcited electrons are trapped on the system, and we can actually see these electrons with the eye, basically. So here you can see the suspension of the carbon nitride. Before irradiation and in the presence of an electron donor, and then we irradiate it, and then we see that the system turns blue, and it has a clear paramagnetic signature as seen by EPR, and this signature is consistent with a pi-centered heptazine or heptazinyl radical. Now, at this stage, let me briefly sort of recapitulate and summarize what we've seen so far. So basically, I mean, the question is, why is the system so special and different from muon-type carbon nitrides? So basically, what we see is a very rapid charge carrier separation after the light, after excitation and formation of an exciton. So we rapidly extract the hole by a sacrificial electron donor. That actually leaves us with the trapped electron on the system. But the trapping is actually assisted by mobile alkali metal ions in the pores that are movable and that can sort of move up to the electrons. That's the picture we have in mind, and really screen the electronic charge on the carbon nitride backbone. So we believe there is there's actually a role of these cations in the pores in screening the electrons that are that are sort of dumped on the carbon nitride backbone by photoreduction. Now, at that point, let me just briefly mention that this is actually quite peculiar because these carbon nitrides are known to be good hydrogen evolution catalysts. And from good hydrogen evolution catalysts, you would actually expect that they don't trap electrons on the backbone or on the carbon nitride, but give them off to the electrolyte very easily to reduce protons. But this is not what is happening here. On the contrary, we're actually trapping these electrons in aqueous solution. And that tells us that intrinsically, these carbon nitrides are really bad hydrogen evolution photocatalysts. They have a high intrinsic overpotential for the hydrogen evolution. And apparently they only get good hydrogen evolution catalysts if we add a co-catalyst. So that is something we need to keep in mind. Carbon nitrides as such are actually quite bad hydrogen evolution catalysts, but that is actually something we can take advantage of. And I'll come back to that in a second. Before that, let me just mention that this process that I've just shown you, the photoexcitation of PHI, the removal of the ions, and then the sort of screening or the sort of influx of ions into the system and screening of the trapped electrons is quite reminiscent of a process that was termed photointercalation by Tribuc in the early 1980s. So Tribuc investigated P-type transition metal ditracogenides primarily, and aguridites and other systems, so semiconductors that were were irradiated, and the light-induced charge carriers then sort of triggered the intercalation of electrolyte ions between the layers in solution. And this is actually a process that is quite similar in this PHI type carbon nitride, where we have a quenching of the holes by a sacrificial electron donor, and there's an influx of potassium ions from the electrolyte into the system. So remember, there are already potassium ions in the system, structurally contained in the system. But we also notice that the influx of ions from the electrolytes is important to stabilize the charge. And so this, in a sense, we picture as a photointercalation process. We believe that what is formed then is a kind of intercalation band, as we would expect for such intercalation compounds. That is then also, you know, responsible for this blue color that we observe. Now, the really interesting question here, and that is actually a question that we're currently dealing with, is there a coupling of these photo-generated electronic charge carriers with ions in the system? So in other words, do we see an optoionic effect here? And optoionics is actually something that has been discovered, I would say, by my colleague Joachim Meyer in Stuttgart, and also Michael Gretzel in MPI type halide perovskites quite recently. So their sort of hole trapping in MPI type hybrid perovskites was described, and it was shown that this is actually an optoionic effect. And so, you know, whether this is a truly an optoionic effect here or not, this is a question I cannot answer at this stage, but what I can say is that what we observe in PHI is basically light-induced changes in stoichiometry. So remember, we have a change in the potassium content of the system. We see actually changes in the electronic conductivity of the carbon nitride upon photoirradiation. We're not quite sure whether we also see changes in ionic conductivity. That is actually quite difficult to sort of verify. And, you know, while keeping overall electron neutrality of the system. And you know, to summarize, what we see here is basically light-induced charge storage. And that is something that we are currently pursuing, or, you know, that we study for various types of applications or properties. And you know, the first and easiest is basically to try and use this temporary charge trapping to decouple the light excitation from the actual photocatalysis. So basically to do something like dark photocatalysis. And what I mean by that is, you know, shown here. So we asked ourselves, is it actually possible to charge up to photocharge the carbon nitride in the light in the presence of an electron donor, then turn off the light and add a co-catalyst in the dark? Because remember, without a co-catalyst, the system does not give off hydrogen, essentially, right? And then can we sort of harvest the hydrogen with a time delay in the dark? And so the answer is yes. What you can see here is a comparison between Melon type carbon nitrides and different PHI type carbon nitrides. So potassium PHI works better than protonated PHI, for example. But what we clearly see is that we can turn off the light and then add the co-catalyst in the dark, and we see hydrogen evolution in the dark. And so this, of course, is only useful if we can decouple the light from the dark phase a bit more. And so this is what we did. So basically, we are increasing the time delay and add the co-catalyst after, you know, hours of turning off the light. And then you can see we have a substantial loss of hydrogen. This is basically all very you know, unoptimized data, but we can also clearly see that hydrogen is also evolved after, you know, 7 hours, 10 hours, and so forth. So we can really include a substantial time delay between light excitation and dark photocatalysis. And that is actually a process that is quite reminiscent of natural photosynthesis. Because when you look at photosystem 1 here, after light excitation of P700, the electrons are shuttled across a complex electron transfer chain or transport chain to ultimately be stored as NADPH. And that is sort of then, you know, the kind of fuel or high energy carrier that is used in the dark reaction in the Calvin-Benson cycle to reduce CO2 to sugar. So here we also have this decoupling, which you also see in this PHI type carbon nitride. Here, of course, it's much simpler because this is just one material where we dump our electrons on. We don't have to sort of you know, transform it into an intermediate and then regenerate the electrons in a sense. But of course, you know, the long-term storage is really the challenge in our system. I guess that, you know, has got clear already from what I've shown so far. And this long-term storage, of course, is necessary when we want to do, when we want to go further and actually use these systems for charge storage. So what we basically see here is that we can decouple light absorption from solar fuel generation, hoping that this ultimately, will help us to overcome the intermittency of solar irradiation. But can we also go further now and create a solar battery where we store the charges for a long period of time and then decharge and sort of regain this electrochemical energy. So this is actually, long story short, this is an ongoing study in our group, and I just very briefly mentioned some first steps in that direction towards a solar battery anode. So what we've done is we've deposited PHI on a transparent substrate, FTO, and by irradiating it, we can see that if we do this for increasing periods of time, so you can see here that the photopotential increases, and we can discharge the system and sort of regain increasing amounts of charge. Increasing amount of illumination then translates into increasing amounts of charge. The charge density is not super high in these systems, so it translates basically to 1 electron per 9 heptacene units in a very unoptimized systems. But we believe that the capacitance can clearly be much more enhanced. Now, we're still struggling to understand really the nature of charge storage in these systems. So this is, I cannot really give you a sort of a conclusive or final description here. What we can see in these cyclic voltammograms is that charge storage depends on the voltage window. I guess that is, it's also not too surprising, and the scan rate. And that clearly shows us that we have different contributions, capacitive and also Faradic or pseudocapacitive contributions to the charge storage. And it's most likely a combination of the two, but the dominant one we believe is a pseudocapacitive, diffusion limited charge storage, so a rather slow process. Nevertheless, it's kind of a hybrid system. What is also interesting is that the ionic species in the pores really, contributes to the ability of the system to store charge. And that is also not too surprising because, we need this, we believe we need the screening of the electronic charge carriers. And so if the cations are too large, too bulky to enter the channels, then we don't see charge storage. So for example, for tetrabutyl ammonium cations, we don't see charge storage. So the size of the ionic species matter. On cycling, there are certainly, problems. We can run a couple of cycles, and, we're pretty confident that actually the loss, especially the initial loss in capacity, really comes from the fact that these PHI nanosheets don't really adhere very well to the substrate. So there's a lot of engineering involved, and we didn't really get around to make perfect thin films that really stick on the substrate, but that's ongoing. Now, the point that I really want to make here is that sort of reiterate is that charge storage in the system, as you can see here, occurs way negative of the hydrogen evolution potential. And that again tells us that this is a system that can be operated in water in principle, and where hydrogen evolution does not really interfere, ironically, in these systems. So this might be a system that is interesting for aqueous solar batteries, perhaps. Now, okay, coming to the last point, what I've shown you so far is basically that charge trapping in the system is possible. And it is highly desirable to have long-term charge storage, especially for solar batteries. That's obvious. We don't want to lose the charge by any kind of lost channels, but we want to permanently store the charge. Now, this is very demanding in the system, and the question is: are there potential applications where this long-term storage is actually not needed, or perhaps not even wanted? And one such application is actually where we use this charge on the system as a kind of fuel. So remember, if we have a fuel, we need to put this in a tank, and we want to store it in the tank, but we also need to release it while we are driving. To propel. ourselves, right? And so can we perhaps use this kind of charge trapping for propulsion of PHI particles? And so here we're now in the realm of light-driven micro swimmers. This is a bit of a stretch now, and let me very briefly sort of introduce you to this basically field. So micro swimmers or autonomous, that is actually the type of systems we're looking at now. Autonomous micro swimmers can be propelled by two basic mechanisms, and hybrid mechanisms actually that are hybrids of those two. One is self-diffusiophoresis and one is self-electrophoresis. Self-diffusiophoresis so triggers motion by the buildup of a concentration gradient across the particle surface. And that actually then translates into propulsion of a particle basically by exerting chemical pressure. Now, this asymmetric or buildup of a concentration gradient around the particle can be achieved by making Janus-type particles, like shown here, where we have asymmetric surface reaction. So, for example, we have a surface reaction only on one side of the hemisphere or one hemisphere. Like, for example, hydrogen peroxide decomposition at this platen cap. Now, self-electrophoresis is very closely related. Here we have a buildup of an internal electric field, which sort of drags along the counter ions across the particle surface, and that then gives rise to propulsion basically in the opposite direction. And so, again, this type of motion is induced by a chemical reaction on one part of the surface, or one hemisphere of the surface. Now we can have hybrid versions of the two. In fact, most propulsion mechanisms are hybrids, and we can induce these surface reactions by light. So what we're looking at here is now light-induced photocatalytic reactions on the surface of these microswimmers that drive motion of drive the particles that induce propulsion of the particles. This is actually, long story short, our colleagues from the Max Planck Institute for Intelligent Systems approached us, and they were looking for specific types of, and especially, let's say, biocompatible materials that could be used for light-induced propulsion. And they asked if we, being interested in photocatalysis, if we have interesting systems for them, and that we would like to study together. And so we said, well, yes, we have PHI, and of course we were intrigued to see if this, this kind of solar battery type behavior, this charge trapping behavior, would also play out when we use these as microswimmers. And so what we did is we capped these particles. So we made Janus PHI particles. We kept them with a platinum or also gold or silicon dioxide cap. So actually we tried various caps. And what we see is that, in fact, if we shine light on these particles, I hope you can see the movie. So this is now in 5% methanol. These particles swim. So there's clearly light-induced swimming possible by using various electron donors, methanol or for methyl benzyl alcohol, and of course also hydrogen peroxide, but at very low concentrations actually. So this is a very dense slide. Let me just briefly say that we've tested swimming with different cap materials, including silicon dioxide, and we see that even using silicon dioxide, these particles swim. Now we know that even using no cap at all, is sufficient to propel the particles if we're, introducing sort of by, shining light asymmetrically, just from one direction, by inducing sort of an apparent asymmetry in these particles simply by having light coming just from one direction. That is enough to propel the particles. We also can make them swim in different media, not only those shown here, but we can also make them swim, for example, in glucose. and simply fuels that can serve as a sacrificial electron donor under irradiation. Now, we also noticed that competing surface reactions, like shown here, where we have a reaction on the platinum side, so hydrogen peroxide decomposition, and also light-induced hydrogen peroxide decomposition at PHI can actually, so these surface reactions can compete and can slow down the particles. So that is, for example, shown here, where the platinized system is actually slower than the gold system, where hydrogen peroxide decomposition is not as efficient. And that is actually, something we need to keep in mind when it comes to, to sort of solar battery type swimming, as I show you in a minute. What we also noticed as a side remark is basically that, most likely in these systems, if we look at them under ambient conditions means there is actually oxygen in the solution. Then we do not observe hydrogen evolution as is normally assumed. So normally, when you look at the literature and they use, say, platinum capped titanium dioxide, it is assumed that hydrogen evolution is one source of propulsion in these systems. But what we could clearly show is that, before hydrogen can actually be evolved, oxygen from the environment is consumed by being reduced. And that is most likely the dominant propulsion mechanism along with the oxidation of the fuel. So that's more or less as a side remark. But coming back to the question, can we actually observe something like photocharging on these systems? And can we charge them up in the light and then make them move or continue to move in the dark? And there's actually, one scenario where we could imagine that this happens. What we need is we need to have a buildup of electrons on PHI, in spite of the fact that we have oxygen around that can actually act as an electron acceptor. And so normally one would assume that, once there's oxygen around, the blue state is not maintained because the electron is simply accepted, basically, or taken up by the oxygen. But if we have this asymmetric, surface reaction, then we can imagine that if hydrogen peroxide oxidation of platinum is very efficient, the electrons from the platinum can be used to quench the holes on PHI. And that can then lead to a pileup of electrons or accumulation of electrons on PHI. So this is at least a sort of, a theoretical possibility. And in fact, what we observe is pretty much exactly that. So here you see a swimmer a swimmer in the dark. So we have the light turned off, and now we're turning on the light, and the swimmer, as you can see, moves. And now we're turning off the light, and the swimmer continues to swim. So this is shown perhaps even more clearly here, where we have now we have the light on, and now we turn it off, and you see that there's a charge decay that goes on for a very long time. So we turn off the light, and still the particle moves essentially ballistically. And so to sort of put this into a graph, what we find is then when we irradiate the system for 30 seconds, the particles move for up to about 30 minutes. So this is really a very interesting phenomenon that has never been observed before in these micron scale, micro swimmers, that we can basically charge up the system like a battery, and then we turn off the light and the particles continue to swim. And we believe that is due to the slow but continuous release of charge of electrons taken up most likely by oxygen as a source of continuous propulsion. And so I'm basically at the end now. What we've done lately is to be very brief here, we've been looking at different features in the system. For example, the fact, a quite surprising fact, that these micro swimmers are extremely ion tolerant. So normally you would observe that colloids cannot swim in high salinity environments. So in high ionic strength environment, even ionic strength that are just a few millimoles. are to sort of make the movement break down. This is not the case here. And so we can have these particles swim in biological media, for example. And that, of course, also then enables us, and that is something that we've just done, to use them as drug delivery vehicles. So interestingly, they are quite porous and they take up huge amounts of the anti-cancer drug DOX. And we can even trigger the release of this drug by light. We've also been looking at other features of these PHI systems. Surfaces, can we sort of change the surface polarity? Can we add surface functional groups, for example, that would interact with certain drugs and so forth. And so that is basically the sort of type of follow-up research we're currently doing in this regard. And that brings me to the end. I would like to thank you, especially for sticking around for a long time and really sort of being so patient. But I would also, of course, and especially thank my group, a bunch of really dedicated and really sort of engaged young scientists that did all the work. Of course, also thanks to all the funding agencies, especially the ERC. And again, thank you for your attention, and I'd be happy to take questions.
Thank you so much, Bettina. Round of virtual applause. I'm really fascinated by these micro swimmers. Maybe before I go into the questions in the chat, how big are these little swimmers? You had a scale bar in the videos, but I don't think you said how big the scale bar is.
It's these are fairly irregular shaped and sized particles, but round about a few microns. Roundabout.
Okay.
So 1 to 5 roughly, but it varies. So they are not monodisperse.
Okay. Thank you. Okay. Shantanu had a question, but he wants to go last. So we can start with maybe Alan. Do you want to unmute yourself and ask your question if you're still around?
Yeah, sure. So my question was basically on the nitrogen COF. If you could share a little bit more on how you introduce nitrogen into the structure of that material, that would be great.
So I assume that you're talking about, well, maybe I should go back. So you're talking about the covalent organic frameworks that are based. So this AZ and COF series, is that correct?
Yes, please.
So, I mean, this is this is fairly straightforward. So basically, we're just using different types of building blocks here. So basically, we have 4 different building blocks, and these are made by bottom-up chemistry, organic synthesis. So these are simply 4 different building blocks with varying amounts of nitrogen in the central arrow ring. So the nitrogen is there, and then we link these building blocks. I think I didn't mention this, by hydrazine. So these are all, these are 4 hydrazine linked COFs that simply have different numbers of nitrogen here in the central arrow ring. So
I get it. Thank you.
Yeah.
Yeah, I didn't know nitrogen was part of the structure already. Thank you.
Yeah, it is.
Okay, thank you. Then there's a pretty straightforward question. Can these materials be used for solar heating? Now I'm not sure which materials. I'm assuming those were the swimmers at the end.
Yeah, well, so I guess, what I can say is that we haven't tried. Of course, in principle, what you would want for solar heating is a small band gap. And likely a smaller band gap than we have in these systems. So the carbon nitrides have a band gap of 2.7 eV roughly. The COFs, of course, are more tunable in that sense. So we could also, of course, using different building blocks, we can pretty much play around with the band gap and make it smaller, make it absorb more, IR. Or towards the IR. So I think this is feasible. The question I would have, or the doubt I would have, is basically a bit, towards the stability of these systems. there might be issues, but in principle, the thermal stability of COFs is not too bad. I would say roughly between 300 and 500 degrees centigrade should be fine, depending on whether you have an inert environment, so inert gas environment or oxygen. But long story short, I would say, it would be interesting to try, but I think one would have to play around with the absorption.
Okay, Stuart, I hope this answers your question. If not, please speak up.
No, that's fine. Thank you very much, Professor.
Awesome. Okay, then I would say Shantanu is next, if you want to go ahead and ask your question.
Yes. So my question was like, at the beginning you showed the photoelectrocatalysis, right? So, and there you showed some delta G, that's 2.46 electron volts. So you need 2 electron hole pairs to overcome this energy difference. So my question was like, what is the recombination rate that you have? Because recombination is a very important factor. So.
Yeah, I cannot give you a recombination rate. Of course, that depends a lot on the system. And it's also very difficult to figure this out. I mean, of course, it depends on also how you engineer the interfaces and make sure that, you sort of prevent recombination from happening or not. So an intrinsic recombination, I cannot really give you. What I can give you is a sense of the photoluminescence lifetimes, for example, that would sort of relate to this. So basically, and here again, it very much depends on the system. So for example, when we look at the carbon nitrides, or COFs are actually fairly similar, most of them. We would look at photoluminescence lifetimes in the low nanosecond range, even below nanosecond range. What we see is that that's actually a recent study that in carbon nitrides and PHI, we can actually distinguish between lifetimes that are modified by charge trapping and those that are more bulk or intrinsic. And the intrinsic ones are typically shorter in the sub-nanosecond range, and those that are sort of modified by the traps are longer. There are a couple of intricacies that we don't quite understand, because in transient absorption, we see actually much slower intrinsic decays on the microsecond range. And I guess that is due to different types of traps. And it also depends basically on your instrumental technique and whether you are able to probe the whole range or just certain ranges, and then you see basically different convoluted processes. But so for COFs, I think we're in a similar ballpark. Lifetimes on the nanosecond scale, low nanosecond scale.
Okay, and what was the quantum efficiency of the COFs material?
It varies a lot. Mostly, I mean, so most of the, for example, actually that one that you see here, these NX COFs, they have very low quantum efficiencies, very low. So low that we don't really dare to quantify them, really. So they are not very emissive, not at all. Mm-hmm. But it depends on the system. Of course, other systems can be very different.
Okay, so my another question was like, are these materials have these materials used for CO2 conversion to fuels, or are there any?
That's a very good question. So yes, COFs are now, there are quite a few works now out there using COFs for CO2 reduction and also carbon nitrides for CO2 reduction. We ourselves haven't really looked at this in detail yet. We are currently starting now to do this. It's interesting, especially for the carbon nitrides, I would say, but it's very challenging also. I mean, as you might be aware, selectivities and also activities are low. But so long story short, there are works out there where this has been done and successfully done.
Oh, okay. And my last question was like, do you have any plans to study the mechanisms by using in situ transmission electron microscopy techniques?
So we actually, or our institute just got an in situ TEM sample holder where we could, in principle, study these things. But I think we're a long way to go there, because especially for the COFs, also for the carbon nitrides, but especially for the COFs, we're having a hard time to do just simple imaging, simply because they are very sensitive to the electron beam. And then imagine that you do in situ. I doubt that this will happen anytime soon, but of course it would be very, very interesting. But there are many things that we need to sort of get right in order to do this.
Yeah. Thank you very much.
Okay.
It was a great talk.
Thank you.
Okay, do we have other questions for Bettina at this point?
I had a
Yeah,
question.
Truman can go, and then maybe I will.
Truman, go ahead.
Thank you. Thank you for the great talk. I was wondering, when you were speaking about the time delayed addition when you were turning the light on and off, could you go to that slide?
Sure.
I think I might have missed what you think the primary mode of the charge loss was after turning the light off.
So we believe actually the primary mode, and I always feel a bit uncomfortable showing these data because they are so totally unoptimized. So these were actually, I think that's what you're referring to. So these were our very first data that we got a couple of years ago on the system, and so we just basically realized what's going on, and then we did this, and we never really looked into optimizing it or really also getting to the bottom of what's happening here. So long story short, what we believe is the primary reason here is simply leaking of oxygen into the system. And if oxygen is in the system, then oxygen will act as an electron acceptor. And so, this is a likely explanation. I don't think it's the only explanation, because that is something, you could control. And I'm pretty sure that, we also have done other experiments that sort of tell us that there might also be other intrinsic recombination, or let's say loss channels that can contribute to this loss of hydrogen.
So you don't have any measurements where you sort of like constricted the amount of oxygen entering the system and observed whether the charge loss was either greater or less?
Well, no, of course. These were done by trying to really exclude oxygen. This is we just, apparently we didn't do a good enough job in doing this, but it's not in air or something like that. We try to exclude oxygen, but we haven't done any, and I guess that is your question, we haven't done really any systematic study on finding out what is exactly the loss channel here. It might be a conglomerate of things, and we really need to look at this in more detail, but this is not, it hasn't happened so far.
Do you have any plans to study this loss mechanism do you expect it to change as a function of temperature? Do you think that might affect it, or do you just have to do the measurements and find out?
I think there might be various loss channels. Temperature might actually, this is something we didn't immediately think of. I guess it would be an interesting parameter to tune. I wouldn't expect that temperature would sort of influence the system heavily, but I might be wrong. I was rather thinking of, chemical reactions that might go on in the system. I was also thinking a lot of perhaps, spin correlations. Well, that is something that might not necessarily lead to a loss in hydrogen in the end, but and their temperature dependent measurements would be extremely interesting to do. I think this is really, this is a point that we need to look at, and we need to understand better what is actually what is the loss due to. We have a sense that oxygen is a problem, but it's probably not the only one.
It's still a really interesting result, and that summarizes my questions. Thank you.
Okay, welcome.
Yeah, I guess you're running short of time, but let me see if Bettina can maybe briefly answer. Thanks for a great talk, Bettina. And I'm actually intrigued by these micro swimmers, because they are micrometer scale, as you said, and there might be applications where you may want to sort of align them or make them move in a specific direction only and not perfectly random. So is there like a way to sort of propel them in a specific direction?
Yes.
And what could be a possible technique for that?
Yeah, there is. Actually, I skipped over that far too quickly because I was running out of time. There's actually a very simple one, which is shown here basically. So these particles swim towards the light. So that is one mechanism of, of sort of directing them, which is known as positive phototaxis. The exact reason, there could be positive and negative phototaxis. Some particles show phototaxis, some don't, and that typically is a convolution of zeta potential of these particles and swimming mechanism, and little is understood there. But another way, and that is actually something we've done with these particles and which is very simple and very standard, is to put a layer of nickel below the platinum cap. And probably you wouldn't even need the platinum cap, and then you can simply do magnetotaxis. So you can guide the particles magnetically in a magnetic field. That is something that works very well for these particles, so that's not a problem. There's also thermal effect and thermal effects that can play a role, but that's a bit more difficult to control. So I think magnetotaxis and phototaxis are the two mechanisms of choice.
Oh, thank you. Yeah, that's good.
Okay, I think we should probably close this. Bettina, we don't want to take up all of your Friday night. Thank you so much.
That's totally fine. Thanks for having me.
Thank you so much for a wonderful talk. Thank you everybody for coming. Thank you everybody for continuous support of the seminar series. And as I said, we will go into a summer break, and hopefully we will see all fans and regulars back next semester. We enjoy hosting this, and yeah, with that, everybody have a good rest of your day.